Hello everyone. Today's topic is applications of exponential functions. And we figured what better way to start than talking about the exponential function that is a part of our everyday lives right now. We are living it. So if you can see on this page here that we have a graph right here, and it's from an article, McLean's article called Coronavirus in Canada. These charts show how our fight to flatten the curve is going. So I would like to ask you, what type of function is this? And obviously our topic is exponential functions. So you can really see clearly that this looks very, very, very similar to an exponential function that you just learned the other day. So to answer our own question here, this is an exponential function. It's growing exponentially every day, which is the whole reason why we're staying home in the first place, right? So my next question is this growth or decay, right? Exponential growth or exponential decay. You can tell just by looking at the way that this exponential curve is facing that it is exponential growth. And it's not that we are trying to make it decay, I guess, but I guess the question is, how do we flatten the curve? What does that mean to flatten the curve, right? This exponential function is going like this, and it's getting bigger every single day. We want to make it so that, nope, not you. It's growing, but right now, but we want to make it so that it starts to not grow anymore, right? That as our x values or the time passes and our time gets bigger and moves on, that the growth slows down. So instead of growing bigger, it starts to grow less and less and less and flattens that curve. So you keep hearing that every day, and if you didn't understand it before, then you definitely do now. And that is some exponentials that can apply to our everyday life. But now we're going to see some type of questions that could be found in your textbook so that you're able to understand how do we work with these equations. So for growth, something that you might want to think about and remember is that our base happens to be usually 1 plus the rate. So that's going to be our base in our in that bracket that goes to the exponent of x. And the rate, you usually have to write it as a decimal. Even though they give it to you as a percent, you have to change it to a decimal first. And we'll see that once we take a look at this question. So in 1996, the population of a small town was 1,250. The annual growth rate is assumed to be 3% since then. So that's our question, and we're going to take a look at 3 parts. Part A says, determine an equation that models this growth given the number of years since 1996. So that's kind of always your first place to start, is make an equation so that you can use it and plug in numbers to answer your question. So the important things to note here would be, I'm going to underline some important things there, this here and this here for now. So we know that our equation, we can make it f of x, we can make it whatever we want to as long as we really define it. So I think I'm going to say that p of x is going to be our population, and x is going to represent the number of years since 1996. It is important to establish your variables. So let's go with our just general function. P of x equals to a base to the power of x. It's kind of like our starting point here. And the reason why this starting point is important is because a right here, the number that goes in front is going to be your initial value, or like your starting point. So if it gives you an initial population, that's what you put it in. If it gives you an initial amount of a substance, that's what you put in there. And for your base, like we said before, our base is going to be, since it's growth, we can tell it's growth because it says the population is growing, as 1 plus the rate. So let's put that together and make it our equation. And we're going to say P of x equals, it tells us that our initial population in that year and our starting point, even though like 1996 isn't the beginning of time, it is our initial like starting point in this particular question. And a lot of questions tend to do that and try to word it that way to trick you, but it tells you that it's kind of our starting point here. So the initial population is 1250, so that's going to go here. Our base is going to be 1 plus our rate. Rate is 3%, which as a decimal is 0.03 to the power of x. And we just want to make sure that that's the most simplified possible. You can just add those numbers and get 1.03 to the power of x. So that's part A. Already done. You just made your equation. Now we have to use it. So B says determine the population in 2007. So do you think that I could just say, you know what, I want the population of 2007, so let's put it in there and put it as my x value? You would think so, but no, that is a big X. Why? Because our X is, let's go back up here, the number of years since 1996. So how many years has it been? You can do the math in your head, or you can do 2007 subtract 1996 to get that it's been 11 years. So that's what's actually going to go into your equation. You are going to say population 11 years is 1250 times 1.03 to the power of 11. So now I want you to try to plug that into your calculator. Pause it, plug it in, because people often make the mistake of just doing their math left to right and not following BEDMAS, and they'll do 1250 times 1.03 and then do the exponent, but that is definitely breaking BEDMAS. You want to do this part first, 1.03 to the power of 11, and then multiply. Or if you have the calculator that you can kind of see everything all at once, then you can plug it in and it will do it for you. Either way, your final answer should be 1730.29. Doesn't really make sense to have 0.29 of a person. So we're going to say the population is approximately 1730 people in the year 2007, which again is still old for us. You can expand that and ask the question to be what's the projected in 2020, right? It doesn't matter. You just have to change the number that you plug into there. And finally, part C, we can go back up just to read it, says, in which year does the population reach 2000? So now they're giving us the population, which means that we actually get to plug that into the population side of the equation, which is the left side. So population of 2000 equals 1250 to 1.03 to the power of x. So we're trying to figure out how to get x by itself, which is really tricky here, but we can start with what we know to try and get closer and closer to getting x by itself. And we'll divide the thing that's multiplied in front of our base. So if we divide both sides by 1250, at least we can get that out of the way. And you end up with about 1.6 equals 1.03 to the power of x. And this is where it just ends up being a little bit of guess and check right now, because it's not a grade 11 concept to know how to solve for x here. So sometimes questions in the textbook might ask you that. You just got to guess and check until you get closer and closer and closer. So again, you can pause, do your trial and error. In the end, you'll get approximately between 15 and 16 years since 1996. So it would be between 2011 and 2012. So that one's going to be fun. It takes a little bit longer. There is a quick way to do it, but we don't learn that this year. You get to wait and have fun learning that next year. So we're going to do one last example here just so that we have an example of decay. So in decay, it's going to be the opposite, and we're going to say that our base will end up being 1 subtract the rate. And remember that it is a decimal. So in this question, it says a new car costs $24,000. It loses 18% of its value each year after it's purchased. Another word to call this, and like this is a real life thing, your car loses value the moment that you buy it pretty much. It's called depreciation. So the same thing of a car losing value also is depreciation. All right, determine the value of the car after 33 months. So just like we did before, we're going to make an equation first to start it off. You could do P again, but we said P was for population. We could say this is V for value. We could say V of X is the value of the car, and x is the number of years. And we need to say that's number of years because it tells us the percent after each year. So we're going to make that in years. So to make our equation, again, we have a times our base to the power of x. And our a, again, is going to be the initial value. And we know the initial value of the car is $24,000. That's too many. There we go. And our base is going to be 1 subtract the rate. And our rate here is 18%. So 0.18 to the power of x. And we're going to make that look a lot nicer. We don't actually need units in our equation. So 24,000 multiplied by 0.82 to the power of x. And this makes sense because if your base is a fraction, that means you're multiplying by a fraction multiple times. And it's anytime you multiply by a number less than 1, or between 0 and 1, your value actually gets smaller. So it makes sense that this is now a decay because every value, as your x's get bigger, makes your overall value smaller. So we want to know the value after 33 months. So we said our x is in years, so we need to find out 33 months divided by 12 is going to give us our years, which is 2.75 years. And that's what we want to put in there. So if we keep going here, we will have 24,000 times 0.82 to the power of 2.75. Again, you can plug that into your calculator, and your final answer is 13905. We want 2 decimal places because it's money. So you should have 91. You can make yourself a therefore statement with units and say after 33 months, the car will be worth $13,905.91. Hope that helps with some of those application problems. We will go over more during our weekly tutorials.